everybody. On behalf of Kathy Whitlock, who unfortunately was unable to make it today, I'm very pleased to introduce Dr. Stephanie Ewing, who I think all of you know, but want to give a nice introduction for her. She's the co-director, she's an assistant professor in the of soil biogeochemistry in LRES. She's the co-director of the LRES Environmental Analysis Laboratory and is affiliated with the MSU Environmental Hydrology Group, which I was excited to learn about, actually. So I think that's a nice group that feeds into the Water Center. She received her PhD in 2007 from UC Berkeley, her MS from UC Davis, and she went to undergrad at Oberlin College. Her research focuses on the influence of soil processes on global biogeochemical cycles at the landscape scale, which is a bit of a mouthful. But she is working in the Judis River watershed looking at elevated groundwater nitrate levels. She's also working in the northern Great Plains looking at soils, plant communities, and bison. And she's working in western Alaska looking at methane and CO2 exchange in permafrost soils. Her dissertation and postdoctoral research focused on soil-atmospheric interactions, and I was particularly interested in her postdoc research where she worked at Lawrence Berkeley National Laboratory using precise measurements of lead isotope ratios in airborne particles from urban and coastal sites in California to show that as much as 98% of airborne lead at urban sites is originating in Asia. So with that, I'm looking forward to your presentation, and thank you all for coming.
Thanks. Thanks for the opportunity to talk to you again today, and also to wear this jacket that I haven't worn since I interviewed. It's a special occasion. So I'm going to speak along the lines of this theme, the connection of soils and streams. And the image that you're looking at here is from central Alaska. This is actually a Nick Point location at the edge of a burn zone. And you can see very actively that there is DOT and sediment load here that is reflective of that connection. All right. So thinking about the response of terrestrial ecosystems to climate change, we're often thinking about that in the context of disturbance regimes. And so in many cases, those disturbance regimes are interacting strongly with soils. Soils are the thing being disturbed in many cases. And the currencies at play are organic matter, nutrients, water, sediment, things like that. The kinds of questions that I would ask in this context are, how do soils in the context of landscapes and landscape legacy and ecosystems, thinking about resilience, mediate the storage and flux of these currencies? And then as we think about perturbation and disturbance, particularly in the context of climate change, how do we understand what groundwater and stream chemistry through time and in specific landscape contexts are communicating to us? So my talk will have two parts. The first part I will summarize some work in Alaska recently published. And the theme here is permafrost vulnerability and resilience. And here I'm thinking about the loss of stored sea with permafrost thaw, the loss of stored carbon. In part two, I'll spend more time thinking about water quality, soil health, and Montana wheat production with focus on the Judis Basin, as Sandra mentioned. And here the theme is loss of stored nitrogen with cultivation. So when we think, the reason that we care about permafrost and climate feedbacks are because of the enormous amounts of carbon stored in the Arctic. This is not news. Half of stored carbon on land is in permafrost soil, and most of that is perennially frozen and subject to thaw of very large potential feedback, climate warming. What this map is showing, and I can't point to it, right? What this map is showing is the distribution of continuous and discontinuous permafrost in North America, and then the distribution of carbon. I realize you can't read the legend there, but you get the feeling from this map of the fact that the very large amounts of carbon stored in the Arctic are not distributed just by latitude. In fact, there is a landscape context or a depositional environment context that dictates those inventories. And so as part of postdoc work with the USGS, I undertook some work looking at upland and lowland sites in central Alaska. And this was NSF-funded work through the Carbon Water Program. In upland sites, we focused on the kind of environments where this core came from on the right, deep aeolian silt with syngenetic permafrost and very high ice content. And by syngenetic, meaning permafrost table that propagated up with deposition of loess through the process of insulation of the falling loess. Upland environments where we predict that the outcome of thaw will mainly be carbon turnover as CO2. Whereas in lowland environments, and that's the star in western Alaska, so Hess Creek is more north of Fairbanks, Innoko Flats is a peatland in western Alaska. And these cores are here to illustrate the depositional context where we have accumulation of a peatland over reworked lacustrine silts in a lowland setting. And so in that lowland setting, we hypothesized that permafrost thaw would lead to wetter conditions and net positive radiative forcing by virtue of methane production rather than CO2 emission. So when the lowlands thaw, they get wetter, you get methane. And this is, of course, in the context of this broader question, what are the climate feedbacks of a thawing Arctic? And how will that landscape legacy mediate the response of these systems to a warming atmosphere? So can we think about landscape context and landscape stratification as a way to understand that? We use the approach of a chronosequence. So this is a sequence of peat soil sites that varied with respect to time since thaw. And these are collapsed scar bogs. So we have a sequence of 4 bogs that is the primary focus here, 4 bog ages. The left photograph shows the frozen plateau situation where we have maximum elevation due to ground ice, forested, and a moss community dominated by feather mosses and sphagnum fuscum. When you form collapse scars in that environment, you get this beautiful transition to sphagnum riparium, this bright green color, and you form small features over times of 10 to 20 years. And the times here are by radiocarbon dating of the cores, which in itself is a challenging undertaking. In intermediate bogs, so as thaw progresses, after 20 to 100 years, you get these more extensive floating mat situations of sphagnum riparium and sedge, importantly. And then with succession over time, you move to, after 500 to 1,000 years, what we're calling old bogs. These have a more solidified peat mat, the maximum degree of elevational collapse with thaw. And again, that's because of the ground ice content. And so in the smaller panel, maybe I'll point here. Oops, no, go there. In this smaller panel, what we can see is peat elevation. And so I'm showing you the fact that the land surface is sinking, as we saw, as illustrated in these photos, and that the character of the peat is changing. We're transitioning from this sphagnum fuscum-dominated forest peat into this riparium-dominated bog peat. And what we see over time is a significant transition in the ratio of those things. We replicated landscape units here and observed, as you might expect, a high degree of variability in the carbon stocks, which is what is essentially represented here, but that ratio did increase. Okay, so we used, and I should mention, this is Carmel Johnston, who completed a master's degree with me. This work has just been published in Environmental Research Letters. And here she's making a methane flux measurement in a closed chamber. We were limited in our ability to make measurements by what we could put into the floodplain to get out there. So here are the flux results, just out in the environmental research letter. So on the left, I'm showing methane efflux, and on the right, NEE. We undertook 3 field campaigns to try to capture the range over the growing season, and I'm showing you, again, the 4 site ages of the chronosequence, frozen, young, intermediate, old, as well as a fen location for comparison where we have flowing water. And what we see is that we primarily have carbon CO2 uptake when we make our NEE measurements at these sites. But we also have methane emission at the intermediate site in particular. So focusing on the green symbol, we have a peak in methane emissions at the height of the growing season at the intermediate age sites. And at the same time, we have a lower NEE number, meaning more uptake of CO2. So just representing that in the context of these peat inventories, we have maximum methane emission and the intermediate features, but we also have increased CO2 uptake. And you know, in order to scale those arrows or think about them in the climate context, you need to think about radiative forcing. So that's what's shown here. Young, intermediate, old bogs, radiative forcing as femtowatts per meter squared over time. Does the methane win? So methane, we often think of as having 75 times the greenhouse gas warming potential of CO2, right? But in a bog context, we're not thinking about a one-time release of methane. We're thinking about sustained emissions. And so this approach, which is summarized in this paper by Steve Frolking, allows us to compute the net forcing effect. And so what's shown here is CO2 effect, generally cooling, always cooling across the chronosequence in red. Methane, always imparting some positive forcing, but the balance is only in the positive for the first 50 years in the intermediate bogs. So we get this transient warming, net warming effect from those features. It's also important to add, and I'm throwing this in, although it wasn't part of something that we included in the paper, because there's been a lot of work lately thinking about the role of nutrient release, and in particular, available nitrogen release when you, in the context of disturbance. And so with thaw, it's being increasingly observed that you release nitrogen. We saw that in these collapsed scar bogs, but mainly at the thaw edges more than anywhere else, at the active edges of thaw where collapse was occurring, kind of the soupy perimeter. This is very much in agreement with some recent work that has come out in Science by Katie Walter-Anthony et al. They were working on Siberian thaw lakes, and they saw a similar effect where you have over decadal timescales or short timescales, release of nutrients, strong emission of methane, but eventually that's compensated for by increased ecosystem productivity, uptake of CO2, and in effect you get back to where you started. So we observe this transient effect, a transient episode of methane efflux with time since thaw in this environment. And yet when we think about how we understand this chronosequence approach, we have to remember that we're looking back in time, and essentially it's a moving target because we have the ongoing, press disturbance of climate change that is probably going to change the playing field in terms of how the ability of these ecosystems to respond and compensate for disturbance effects. So a nice example of ecosystem resilience, how long will this hold up as we confront changing climate? All right, so now I'm going to switch to work in Montana and consider the effects of, think about cultivation of temperate grasslands over the past 100 years. So thinking here, thinking here about nutrients and loss of soil organic matter, this is something that we commonly observe with cultivation in agriculture. In fact, we take advantage of it. So we know there's a nitrogen pulse that happens when we break ground in grassland ecosystems. It's just something that happens. And what occurs then is you get more productivity out of your crop as a result. But how does that play out in groundwater and streams? And this is a recent paper by USGS authors thinking about the geometry of landforms that might dictate residence times and thus communication time of released nitrogen into streams. This is part of a bigger issue that has been communicated about in a number of ways. This is Canfield et al. 2010, a figure I like to put up because it gets to the really big picture. And that is to say that if we think about natural fluxes in purple and anthropogenic fluxes of nitrogen in brown, we see the magnitude of the perturbation. We're loading up continents with anthropogenically fixed nitrogen, and so far we haven't seen that nitrogen come out in land to sea transfer. So we're waiting. How is it going to show up? When is it going to show up? And how is that going to play out? So this is the Judis Basin, the Judis River watershed in central Montana. We were interested in this area because of Adam Sigler's work there as part of MSU Extension through doing well testing. And what was observed in an MDA report and some of the well testing that MSU had done was that nitrate levels were persistently high in this location. This is an area of dryland wheat, so non-irrigated wheat and livestock production with common fallowing. So a 3-year rotation, 2 years of cereal, 1 year of chemical fallow, and I'll show you what that is in a second. These shallow aquifers in this area are vulnerable to nitrate contamination because they are quite shallow. Soils have shallow gravel contacts in them. And so there was a rapidly emerging problem, but little adoption of recommended management practices in this area. And so these are the baseline data that Adam gathered in our proposal for this grant. So what we see is high nitrate levels exceeding the drinking water limit of 10 milligrams as N per liter in the blue symbols. And those are commonly associated with these flat alluvial and pluvial landforms in the middle of the basin. I should point out the Judis River is a tributary of the Missouri, and so we're very much upper Missouri watershed in this area. So this now shows adds layers indicating lithology and also the degree of cultivation on these landforms. So the red colors show you that these shallow aquifers are perched on top of underlying marine shales. So these clay-rich, sometimes saline materials that very effectively perch aquifers and keep them close to the ground surface. The landforms here are alluvial fans and strath terraces that are mantled by gravel by virtue of the process of their formation. And then also loess, and it's that loess cap that makes these soils good for agriculture, as is so common around the state. So we focused on particular landforms, 2 strath terraces and an alluvial fan. And in particular, I'll talk mainly about this one in the middle. This is the location of the town of Moccasin, Montana. And we had the advantage of a relatively long-term, since the mid-90s, record of nitrate in a monitoring well managed by the Montana Department of Agriculture on this landform. So the declining groundwater quality, the rising nitrate levels that we observe in this area suggest a need to use nitrogen more efficiently in terms of how crops are fertilized. But at the same time, what that means is a loss of native soil fertility. And it's that leverage that we're using to work with people and think about how to manage this issue in this area. Okay, so here's an example of a soil profile. This is in an uncultivated grassland setting. We get these deep, dark surface horizons. These landforms are at least 10,000 years old. These are high fertility soils, but they also have these shallow gravel contacts. Here's a cultivated profile to go with that one. And I'm just showing this to you to give you a feel initially for how these soils look, and also to illustrate how there isn't a lot of visual change that goes on here, although we can see, and it's really distinct in the field, a residual plow layer in the soil profile. That's there even though since the mid-'80s, no-till agriculture has been practiced. But what's missing here is the inventory of the organic matter. When we take a look at that, we find that there's about 11,000 kilograms of soil organic nitrogen total there. And based on work by Steve Custer in the 1970s in the Hailstone area on soils a lot like this, as well as work in the 90s across the temperate grasslands of North America, we know that 30 to 40% of organic matter is lost with cultivation typically, focusing on the top part of the soil. And what Steve saw was that 1,000 kilograms of soil organic nitrogen shows up in the vadose zone, or if you had a shallow water table, it shows up in the groundwater. And this is just based on comparative inventories of cultivated and uncultivated sites at that time. So it's hard to do total nitrogen by difference in soil profiles. In particular, you have uncertainties around the issue of measuring bulk densities, not straightforward. So we'd like to use the groundwater signal to evaluate nitrogen losses from these soils as a measure of nitrogen use efficiency. And this is just a summary slide to show the broader efforts that we're undertaking as part of this work. I'm focusing on field and landscape scale hydrology, which is Adam Sigler's dissertation work, working with me. We are also looking at effects of management changes on nitrate leaching. That portion is led by Clayne Jones and his student Andrew John. And we're taking a participatory approach to tackle the problem and work with the community. So we're working with producer groups and community stakeholder groups to try to get the research out there as quickly as possible and get feedback from them about their interpretation and their understanding, because ultimately, if we're going to change these patterns, the producers are the ones that need to buy in. Okay, so photos to illustrate how this location looks. These are big, flat landforms. And we're producing cereals, winter wheat, spring wheat, some barley is the spring cereal, and fallow looks like this in the no-till context, meaning weeds are sprayed out with herbicide and there is no tillage at this point, and that's been true since the mid-'80s, essentially coinciding with the invention of Roundup and no-till drills. So here's our well information from that monitoring well on the Moccasin landform. So I'm showing you the landform itself on the top, and this is a great place to study this issue because this is a strap terrace that is incised at its head. So you can see this in the topography that Adam has emphasized here. Streams are going around the top, and recharge of the shallow aquifer on this landform is only through rainfall infiltrating through soils. We also have results from this monitoring well that tell us that since the mid-'90s, nitrate concentrations have gone from 10 milligrams per liter nitrogen up to 25 milligrams per liter, and those filled symbols are our data from 2012 and 2013. I'll show you some 2014 data in a second. So chronically rising nitrate levels, some other stuff perhaps going on there that we could explore, and I should emphasize these are annual averages. So MDA was sampling twice a year, and I've averaged those numbers. These averages represent 13 to 15 samples over the course of the year. And that effort was started with a master's work of Christine Miller, working with me, and has been continued and expanded by Adam Sigler. Okay, so we can think about this pattern as a function of changing inputs. So this plot shows over time nitrogen applied in fertilizer on wheat in Montana. So we've gone from next to no fertilizer additions in the early 60s up to fertilizer additions that exceed yield. So the green symbols are wheat yield as nitrogen for Montana, and these numbers actually line up with other data for the Judis Basin for a couple of years. And so we see a consistent pattern. It's not a surprise. We started out not having to add nitrogen, and now we add more or equal to what we take off in yields. And so it's easy to point the finger at fertilizer in this given this information, but how does that work exactly? So now I'm thinking about nitrate N as a pool. So I've gone from units of milligrams per liter to kilograms per hectare. So thinking about the area of land that this aquifer underlies, and taking the inventory of the aquifer and averaging by hectare, we see that we've gone from 150 to 300 kilograms of nitrogen per hectare in the aquifer. So this involves some assumptions about the dimensions of the aquifer based on well logs, but obviously this is a longer-term problem. Generally, what is put on in a year now is 60 kilograms per hectare. Okay, so now I'd like to show you some results for nitrate dual isotopes. And so I'm going to introduce you to some of the sampling sites that we're using here. We're sampling the creek that is incised into the center of this landform, Loud's Creek, at an upper location, also known as Railroad, and at a lower location, also known as Colon. As I said, we have dispersed recharge at the surface of this landform and discharge through emergent streams and springs. So you can see all these stream channels emerging, and all in this down gradient area you see spring lines. I'll show you a picture in a second. I'll also show you some results for lysimeters that we've installed in the fields where we're comparing management practices. And I'd say that in passing, but it's actually a pretty massive undertaking to do that under a farming operation. See Adam's video on YouTube if you want some more information on that. Okay, the M1 well, as I mentioned. And so we're arguing here, or wanting to test the idea, I guess, that the spatial distribution of land management and soil properties must control nitrate N loading to the shallow aquifer in this context. Here's how the soils vary. So soil properties matter because these gravel contacts can be anywhere from 20 centimeters, actually to more than 70 centimeters, up to a meter. And so the amount of room you have there for water and nitrate storage is quite variable on the landscape. And so if you think about the key controls on how much nitrate might leave the soil profile and leach into the groundwater, I tend to start by thinking about that gravel contact, which essentially dictates the space I have for storage prior to leaching. It's worth emphasizing that we commonly see at these kinds of textural contrasts in soils, fines over gravel, that water will get hung up in the fines because of matrix potential. And so you tend to accumulate water and solutes there until you've filled up the profile. So we've thought about it that way quite a bit in terms of the water balance. So thinking first about the hydrology, I have rainfall as an input and evapotranspiration as a loss. And both of those things impart O18 signatures to soil water. The rainfall is seasonably variable, and the evapotranspiration, we're mainly thinking about evaporation from the soil surface although the transpiration matters obviously a great deal to the water balance. But the residual O18 from evaporation will be isotopically enriched, so that delta value will go up. As water infiltrates, it gets hung up at this contact, and we can sample that water with our lysimeters, which we have placed just above these gravel contacts. It's hard to put a lysimeter in here, but you can do it here. As the profile fills up, we think about that as a primary control on what leaves out the bottom, what drains. We can measure isotopes of nitrogen and oxygen in the soil nitrate pool by virtue of sampling these lysimeters. And think about the N15 as a function of fertilizer inputs, yield losses, but also, importantly, the result of the turnover of soil organic matter, mineralization of organic matter that is going to fractionate nitrogen isotopes. And that one's harder to get a handle on. Denitrification loss here will also fractionate isotopes of oxygen and N15 in nitrate. And so what we see in the residual nitrate is enrichment, higher values, as denitrification happens. When we export from groundwater through the aquifer to streams, we go looking for denitrification loss, and we also think in streams about algal uptake, because these streams are quite loaded with nitrate, and you definitely see algae blooms in the summertime. Okay, so this is a dual isotope plot showing you N15 versus O18. And I'm showing you results from 2012 for the M1 well, Upper Louse Creek, and Lower Louse Creek. This linear array is pretty striking and distinctive, and it implies, as the arrow indicates, fractionating loss. So both isotope pairs are getting heavier, and we know from concentration measures of nitrate that nitrate is decreasing through those samples. And so from that relationship, we can get a fractionation effect of 4.4 per mil. If we think about now what we observe in soils, so these are water extracts from soil profiles in the round symbols, and our lysimeter samples in the blue diamonds, we see that the soils are quite variable. They're all over the map, but they still have a strong indication of this distinct slope, close to a 1-to-1 line that strongly indicates denitrification, probably at sweet spots and to variable degrees depending on your proximity to a sweet spot in the soil. The lysimeters, however, fall out right on top of the groundwater, which is very consistent in and of itself. And this implies mixing. We can also infer from these soil relationships, from the slope of the soil line, that if we assume the same fractionation factor that we saw in the groundwater to stream transition, which admittedly is a stretch, but just as a starting point, and we go from an end-member signature like this, we can calculate a loss of close to half of the nitrate to denitrification. So we see indicators of mixing in the water that leaves the soil profile and enters the groundwater. And we know that to some degree that nitrate pool has been denitrified in the soil profile prior to that transport. And we're estimating again that half the nitrate is consumed. Okay, so thinking about this at the landform scale using a numerical model, and I'm going to move quickly through this, but here we're focusing on inorganic nitrogen in the soil and in the groundwater, as opposed to organic nitrogen, which is represented over here. We're thinking about the change in inorganic nitrogen with time as a function of inputs from fertilizer and mineralization and losses to uptake, leaching, and denitrification. And focusing on that leaching term as all of these expressed as first-order loss with a first-order time constant associated. In ChemFALA, we don't have fertilizer or uptake, so that's a simpler relationship. And then in groundwater, based on the water balance, we interpret a mean residence time of 20 years, and we can think about leaching as an input and discharge as a loss. So fitting that model to the M1 increase over time, I can compute loss constants of 0.4 and 0.45 in the crop and fallow that correspond to the 2013 water balance. What we calculate on average will leave, the amount of water that will leave soil profiles is consistent with those loss proportions. But what happens when we apply these values to the entire period of cultivation? Well, this is what happens. If we think about initiation of cultivation here, and we apply that same model over this period of cultivation, we overestimate what was there in the groundwater at our first point of record in the M1 well. Adjusting the loss constants down to something like 0.1 and 0.17, or exactly that, we get this trend. And so here we match the initiation of the rise, but we don't match the slope. In addition, what you can't see here is that we overestimate soil storage. So I would suggest here that what we might be seeing is potential vadose accumulation or accessing of an unseen pool between the soil profile and the water table that might account for this recent steeper rise. It's also true that we're assuming mineralization rates as inputs based on preliminary observations, and so we're also refining those numbers to get a closer look here. So this is Adam asking, what about seasonal and spatial variation in groundwater and surface water composition across the landform? Shouldn't that be informative? And he followed up on that query by establishing a series of sites that test that idea. So we're thinking about flow going in this direction on the landform. And this is Adam's hydroma interpretation right here, right? And so we're looking at sites that capture that capture progression down flow paths on the landform. Not just surface water sites in blue here, but also emergent springs in the green symbols. In addition, he added a well site, an abandoned, or no, this is a well that he got access to from a private owner that helps constrain how the groundwater is looking within the aquifer. All right, so in general, we expect that what the nitrate dual isotope story really started to tell us was that solutes reflecting variable soil processes are mixed by the process of dissolved transport. The aquifer essentially, in this context, averages that signal. And so in the shallow aquifer, which is itself subject to mixing, we expect to see a relatively stable signal given residence times of 20 years. In addition, restricted timing of recharge could help to dictate that consistent aquifer chemistry, so that averaging in the aquifer. So this figure now shows more detail for the M1 well. And so on top here in blue is weekly rainfall corresponding to this axis. This is water table in the well, depth to water. And this one is nitrate concentration as milligrams per liter over the 3-year period of our sampling. And the first thing that we can, well, there's several things to notice here. One is our pattern of springtime rainfall. That particularly in a situation where you don't have a growing plant at the land surface, where you have seedlings or newly seeded crops, we get recharge that coincides with that springtime rainfall. We also don't see expressed here rainfall events during the growing season, because at that point soil profiles are more dried out. There is more storage available for those rainfall events. And so we mainly see the recharge events, with the exception of this thing that happened this past August. That thing there. Nitrate we were amazed by how stable the nitrate had been over the first 2 years of the project, and then whoops, good thing we sampled for 3 years, right? We suddenly saw some variability. But in general, a consistent and high concentration over the course of this year that we place in the context of that longer-term rise. So it's a large pool, and the small amounts you put in seasonally maybe don't have a lot of effect until they do. Yeah, so springtime recharge. Let's think about that using isotopes of oxygen in the water molecule now. So we were looking at O18 values for O18. Now we're thinking about water. And these data are very much a team effort. The analysis was done by Eric Anderson as an IOE intern in the EAL this summer with support from Jane Clausen. And all of the sample collection and orchestration and site establishment was done by Adam Sigler and assisted by Simon Fordyce and a couple of other great undergrads, Brad Newman in particular. So we see this variable signal, and we can interpret this in the context of the seasonal patterns that we expect for O18. There is a seasonal rise that we expect in summertime for O18 because of warming temperatures. And so we expect these values to do something like this. And so looking at these data, we can, interpret them as essentially representing that seasonal oscillation that we'd expect to see in rainfall O18. Now I've put on groundwater results. So M1 well in squares, the headwater well in the circles, over this 3-year period again. And what we see is the same kind of consistent effect in the O18 that we saw in the nitrate. Very steady values at about -15 per mil, matching the intercept with the rainfall in fall and in spring. So supporting this idea of spring, mainly springtime recharge of this aquifer, imparting an O18 value that is consistent. Where we do see this drop that is remarkably similar to the nitrate is in the M1 well, but notably it didn't happen in the headwaters well. Now I've added the springs. So these are emergent springs distributed over the landform as I showed before. And in all cases but one, they hold the line around this -14 to -17 value that we've observed. And there's one spring at the southern edge of the landform, Pioneer, that drops down at the same time as M1. So we went looking for the cause of this, and now I'm showing you lysimeter results in these little diamonds, and also snow. So these were sampled in springtime, and we see a remarkable correspondence between the snow values and the spring and well values where we saw the dip. So some kind of communication of a snow signal in some locations and in some years. And we can think about why that was in 2014 in particular. The lysimeter values also pop down a little bit, and to me that implies seasonal storage of water. So we might have some of that isotopically low fall water still in the soil profile that influences that value, or it may just be that the snow is melting and is being progressively stored in the soils. Okay, so now this is a dual isotope plot for the water samples, and this shows O18 versus deuterium values, and we have a variety of samples represented here. The blue dots are rainfall. The green circles are all of the springs in aggregate. The brown squares are wells. The snow is here as well. And then we also have in the closed orange circles water extracted from soil profiles in July by Eric in Ja Hu's lab with a lot of support from Ja and her graduate students. And then also some samples of water extracted from wheat roots at that same time in July this past summer. And so what we see is that the roots really line up with the rainfall sample from that day. That's why we ran up there. There had been this big rain event. And the soils are incredibly variable. Okay, and I should step back. I'm also showing here the global mean water line. So we have a predictable relationship in meteoric water between O18 and deuterium that is dictated by vapor pressure relationships in the atmosphere. And we get variation along that line that we characterize as a mean water line. And we can assess that globally, or we can assess it more locally. The lighter gray line is from Butte and work of Chris Gammon. So if we come off the line in that direction, as these samples tend to do, towards to the right, we expect that that is a signal of evaporation. And so Chris has illustrated here how that is a function of both relative humidity in the atmosphere and the degree of evaporation, the amount evaporated. And so we notice that these soil values are off to that side, and that really suggests some amount of evaporation that may contribute to the signal we see in springs, which also comes off the line to the right. What I infer from that in this evaluation is that springs and groundwaters reflect mixing of soil water with rainwater. In July, this water in the soil profile probably doesn't have a lot of influence on recharge, but the fact that the springs come off the line is an indication that you have some effect of evaporation in soil profiles coming into play there and mixing with rain. It doesn't just look like rain. So again, a mixing process and an averaging process that brings us into that -14 to -17 per mil range that we saw so consistently in the O18 values over time. Okay, so I've told you that mixing with water movement through soils results in an averaging process or mixing process that we saw in the nitrate dual isotopes and in the water isotopes. Do we see those reduced concentrations of nitrate? And I should say about the dual isotope results, I'm interpreting a fractionation effect based on reduced concentrations of nitrate in water samples between groundwater and streams. And so I'm being careful to say reduced concentration here because, of course, it's always dangerous to infer loss from a reduction in concentration when you don't know the water balance. So we're working on getting the water balance through discharge measurements and making sure our rating curves are in order for the streams and so forth, and also with landform scale groundwater modeling. But basically embedded in that is the assumption that the water that enters these streams from this aquifer is all discharged from the shallow aquifer, and these streams are nothing but gaining. And so we can interpret a reduction in concentration as a loss. So does this reduction of concentration persist across water and climate years? So here are all data analyzed as of Friday or so for nitrate concentrations and for O18 values over the 3-year period that we've been taking samples. And so we see this persistent -14 to -17 per mil signal in the springs and in the groundwater, with the exception of early 2014. The downstream, this is the lowermost site on the moccasin landform, those values are a little bit higher. At the same time, we also see nitrate N concentrations that are consistently lower, with the exception of the spring that went on in spring of 2014, perhaps involving dilute snow, in the surface water samples. So decreasing nitrate along flow paths, and I should explain, wells on this plot are in brown, springs are in green, and surface waters are in blue, to try to illustrate this point. So we go from wells to springs to surface waters, brown to green to blue. We see decreasing concentrations as a general rule. And we see the seasonal oscillation in the surface water. So coupled with these slightly elevated O18 values here, we could interpret that in a couple of ways. One is that we have some evaporation that's increasing, that's influencing these surface water samples. And another is that we have seasonally enriched water that's coming in through overland flow. We're not just getting water from the emergent springs. So it's got to be evaporation or runoff influencing surface waters. The upstream site, which I'm not showing here, so this is the downstream site, preliminary results from railroad look like they're falling more into this -14 to -17 range, suggesting or implicating evaporation as a process that might be increasing those values. And so if we're thinking about evaporation, we're thinking about a process that would, if anything, concentrate nitrate. And so this reduction in concentration could perhaps be due to that same fractionating loss process that I described earlier. Okay, a couple of conclusions. The groundwater in this environment, in this particularly constrained context of an isolated strath terrace, reflects in a couple of key ways mixing of the soil signal. So we see an averaging of root zone process in the groundwater here. Increasing groundwater nitrate over 20 years reflects arguably not just increasing inputs of fertilizer, but probably mineralization of soil organic nitrogen, particularly during the practice of fallowing. And there's a sentence fragment there. Over winter, meaning the fact that we don't have crops present in the spring exactly when leaching tends to happen. We don't have roots there ready to grab that water, probably facilitates the mobilization of the soil nitrate pool. Recharge happens readily in spring, both because of the timing of rainfall, the timing of crops, and also the nature of these soils. And we see evidence of substantial nitrate losses, both in soils and in streams. And so arguably we're seeing slow chronic net loss of soil organic nitrogen from these soils, although those numbers are always hard to tease apart. And some attention is needed in terms of vado storage here that may contribute to the recent rapid rise of nitrate in the groundwater that we have observed in the M1 well. Okay, so I told you about our work in Alaska showing that positive forcing is evident in lowland permafrost environments. We get methane emissions reducing as a response to thaw disturbance the pool of organic carbon, the very sizable pool that importantly is a potentially huge climate feedback. Our current global experiment with the climate system is testing the limits of that ecosystem resilience that those studies illustrate in those kinds of systems. And arguably response rates, or it seems almost certainly response rates, will depend on landscape context. So how that plays out is really going to depend on those depositional environments that tended to accumulate carbon in the first place. In the Judis watershed, we see that those high nitrate levels in shallow aquifers are a reflection, most likely of soil management practices that are not just a matter of fertilization, but of fallowing over many years in this specific context. They will require years to address with collective efforts, but given actually how thin these aquifers are and residence times of 20 years as opposed to much longer in other places, the response rates in this context may be relatively fast. Not short, but relatively fast if we are able to reduce our inputs. But consequences of the current mega drought for wheat and water markets, as well as changing seasonal rainfall patterns that we don't really have a handle on at the local level, are going to challenge our ability to manage these systems sustainably into the future. All right, thank you to many excellent individuals who were part of this work, as well as funding from USGS, USDA, NIPA for the Judis Basin work. The IOE in particular for funding Eric's summer internship project, and MSU undergraduate scholars for contributing to Simon Fordyce's work that hopefully we'll be hearing more about. He's been doing some diel work in the Judis Basin, working with Adam. Couple key collaborators to mention are our advisory groups in particular. And so that ongoing conversation about the results of our research is going to be interesting to see responses to in the near future. Thanks. Questions? Tony.
So are you thinking of incubation? I mean, your plate's probably pretty full, but I thought of a perfect project for Adam's PhD, which is to do maybe, if he's not already doing, just some incubation experiments to check at mineralization versus mineralization with fertilizer?
Yeah, we've thought about that a bit as follow-up work. Adam's kind of got a lot on his plate already, but it would be an interesting thing to do, and we've actually proposed it to NIFA. We'll see what they say. Other questions? Yeah.
So in your Alaska sites, it's really interesting, that transient effect, and I'm wondering about, if you look further into the future, what do you expect in terms of succession with those bogs? I mean, you've kind of played it out in the future a little bit, but what about 50 years or 80 or 100 or more?
Yeah, the longer-term future that we interpret in those landscapes is that you start to insulate in the old bogs and you reaccumulate permafrost and you jack the area up and the trees return, right? So you go back to the permafrost plateau. If you can't re-aggrade permafrost, then maybe the clue is in the fens, the flow systems. So you have protracted and increasingly extensive collapse that connects into the local groundwater system, and that really drives the state of the carbon in the end. Yeah, so our measurements in the fen there showed sustained high methane production there, but we didn't explore all of the sort of permutations of that context. Others are doing it as we speak, but definitely a hot area, yeah.
Are the high nitrate levels in the Judis River Basin, or the watershed, are they kind of unique to or is this all across the Montana central plains?
We see instances of high nitrate associated with agriculture in other parts of the state, and I think particularly of the northeast corner. There was actually a conference that I mentioned in the Water Center meeting earlier this year about nitrate in water in Montana, because it is such a pervasive problem, and really it requires solutions kind of at the local level. I don't know. Other comments on that, Adam?
These two counties are quite high relative to other